Call security. The second talk of the morning, the speaker will be Volk, and he'll be telling us about the structure of Boolean functions with small spectral mode.
Okay, so thank you all for coming. So just for the credits part, this is a joint work with Amir Shpilka and Avishai Tal. Okay, so this is the title of the talk. Now, so I probably don't need to tell you what the Fourier transform is, right? We're all among friends here. So I just put this slide so we can understand my notation. So I think just a Boolean function is a function from the group z2 to the n into the real numbers plus or minus 1, and then we have those Fourier characters chi alpha of x, which are on orthonormal basis, and we just represent the function as a linear combination of those characters, sum over alpha for every alpha in z2 to the n of f hat of alpha chi alpha of x. That's probably known. So the interaction between the Fourier transform and computation can actually go both ways. You can assume that the function has a low complexity in a certain computation model, and then say facts about its Fourier structure. So an example is like the lineal Mansouri-Nissan paper, which says that any function which is computed by a small depth circuit has most of its Fourier weight lies on the low levels. In this talk, we actually go in the opposite direction. We assume several restrictions on the Fourier spectrum of the function, and then we ask, what does it say about the complexity of function in certain computation models? So I'm going to define what restriction I make on the Fourier spectrum and which computation models I'm considering over the next few slides. So let's start with complexity measures. So there are many things you can define here. I'm going to concentrate on two. So the first is the dispositivity. That's closely related to the open problem John asked yesterday. So dispositivity, where I use this notation, is just the number of non-zero Fourier coefficients, right? Just the cardinality of this set. And spectral norm, or the L1 norm, is just the sum of the Fourier coefficient in absolute value, right? Sum over alpha of f hat of alpha in absolute value. So we'll be mostly concerned with the spectral norm in this talk, as the title suggests, but dispositives also have to keep in mind. Okay, so as usual with this thing, if you just pick a function randomly out of the box, you're going to end up with a function with both large spectral norm and large dispositivity. I mean, that's how random functions behave. So you want to understand, I mean, what does it mean to have a small spectral norm or a small sparsity? I mean, how do those functions look? Let's just give a sort of large family of function with small spectral norm. So if you have a function which is an indicative function or a characteristic function of a coset or an affine subspace or of z2 to the n, then its spectral norm is constant. It's at most 3. So it doesn't matter, I mean, what n is or what the dimension. It's always bounded by 3. So examples for these functions include the end function. That's not usually how you would think about the end function, but it's just an indicative function of 1 point. So it's a coset of the 0 subspace, or the OR function. The XOR function obviously satisfies this property. So all have a bounded spectral norm. And this actually turns out to be a pretty good characterization. So there's the following theorem by Green and Sanders. What they say is, so consider you're given a function with spectral norm A. Yeah, just some real number A. Then what they claim is that you can write this function as a linear combination of indicative function of subspaces, sum over I equals 1 to L, and L is at most this thing, 2 to the 2 to the O of A to the 4th. So you might think it's scary, I mean, this doubly exponential thing, but the important thing is that it doesn't depend on n. So like the only way you can generate functions with constant spectral norm is just take a linear combination of constantly many indicators of subspaces. Yes, exactly equal.
Coefficients are all plus minus 1?
Yes. Maybe you can even do them with all plus 1, but never mind. So that's a theorem. And so again, it shows some characterization of those functions with very low spectral norm. So let's move on to talk about the computational model. So the first thing I wanted to mention is the decision tree, which even if you didn't know, so that's what you have to know. I mean, just a tree to compute Boolean function. On every internal node, you query a variable. If it's 0, you move on to the left side tree. If you 1, you move on to the right subtree. And on the leaves, you have Boolean labels. So this tree, for example, computes the majority function over 3 bits. Obviously, you can compute any function. So you define the depth of the tree to be the longest path from the root to any leaf of the tree. And you denote by d of f the minimal depth decision tree, which computes f. So it turns out the decision tree is not strong enough for us. What we need is sort of a stronger version of it, which is a parity decision tree, which is exactly the same, except that now you're allowed on every internal node to query just any linear function of your input bits. So like you choose a subset S, you query the sum of xi modulo 2, and you branch accordingly. So actually, in our notation, it is more convenient to think about it as if you're just querying chi alpha of x for some alpha. So now the labels are 1 minus 1, but it's exactly the same thing. And we use this notation, like d with parity of f. That's the minimal depth of any parity decision tree for f. So obviously, this is always at most the decision tree depth, because any decision tree is in particular a parity decision tree, where all the queries are just queries of single variables. And we're going to also use this size parity of f, which is the minimal size, where we measure size by a number of leaves. So let's think about the XOR function, for example. So its parity decision tree is very simple, right? You only need one query, one linear query to the variables to compute its value. Whereas, I mean, if you think about its decision tree, it's going to be very large. You always need to query all individual variables in order to know the value of the function. So this parity decision tree is actually stronger than the usual decision trees. Okay, are we good? Again. So let's first state the obvious connection between parity decision trees and the complexity measure I mentioned. So let's assume f is some Boolean function, which is computed by a parity decision tree with depth d and size s. Then I claim that its spectral norm is at most s, which is at most 2 to the d, and its sparsity is at most s times 2 to the d, which is at most 4 to the d. You get this bounds by simply, like, you have a tree and you write the function as a sum of indicators of all the leaves, and that's the bounds you get. And they are tight in such several cases. But again, it's nice to know. I mean, can you get an inverse theorem for this fact? I mean, can any function, I mean, if I give a function with small spectral norm, small sparsity, can you find a small sized or small depth decision tree which represents it, which computes it? So I'm not defining small in this slide. I'm just asking a general question. And well, we're going to have some partial answers. And John mentioned like a major open problem in this in answering this question. So we're going to get back to it. So let's state like several of our results. So suppose again you're given a function whose spectral norm is a. So the first thing we do is that we identify some sort of local structure of f. So we claim that there's some subspace, an Fn subspace V of z2 to the n, with codimension at most a squared, such that f must be constant on V. So again, you can think about it in contrast to the Green-Sanders result. They have this sort of global characterization of f as a sum of indicators, and we find like a local structure in f which must exist for such function. And again, if a is constant, for example, then there must be this really huge subspace such that f is constant on all of these subspaces. Another thing we do is we give a bound on the parity decision tree size of f, which is at most this thing, 2 times n to the a squared. So again, for the case that a is constant, which is quite interesting, it must have a polynomial-sized parity decision tree. Okay, so I mean, you can't balance, or you can't always balance decision trees. So I mean, it's only about the size, not the depth. But yeah, do you have?
You can translate the. You'll get a parity constant size decision tree.
No, the Green-Sanders results that doesn't give a decision tree. I mean, it's only like a sum of indicators. I mean, how do you get?
And each subspace is just.
It's a sum.
Yeah, but that may be like n queries when then it's trivial.
Eventually you have to
Right,
sum.
but if you query the values of all the subspaces, then you know the sum. Then you can just.
Yeah, but I mean, to query the value of all the subspaces, that may be much larger than n,
No, no,
which is.
all the subspaces they want.
In the expansion.
Yeah, so again, they have, I mean, like sum of I equals 1 to L of 1, let's call it UI. So you can query like a basis of UI dual if you want to know what's 1 UI of X. But that may be much larger than n even, I mean.
So they don't give you any guarantees about these UIs they're coding?
Yeah, they give like you may look at proof and try to figure out something, but it doesn't work like out of the box.
Of constant codimension?
No.
No.
It could be the n function. And then
Yeah, so again, this may be like indicator of 1 point. So you have to query n queries to reach it, and then you're already worse than the trivial thing.
You can invent the notion of like a coset decision tree where each guy gets to query a coset, and then they'll give you a coset decision tree of depth 2 to the a to the 4th. But you can't turn that into a parity decision tree very easily.
Yeah, but how do you query a coset that's not maybe binary tree, right? I mean, you could just query which coset of the 0 subspace you're in and just, know the value of the input.
No, it just says whether or not you're in the coset, so it will still be a binary tree.
Okay, yeah, I guess you could do that. Yeah, so again, the Green-Sanders result doesn't give an obvious decision tree, and this does. Next one, we also have bounds on the depth of the decision tree, which is like a squared time log of the sparsity. Remember that the sparsity is the number of non-zero Fourier coefficient. If you're willing to settle for an approximation of f, like epsilon approximation, then for every epsilon greater than 0, we can give a tree of this depth, a squared plus log 1 over epsilon, which computes a function which is an epsilon approximation for f. And you can also learn this efficiently. Obviously, this is informal. I'm going to get to what I mean by learning. But let's take this statement as is right now. And finally, I claim that everything basically holds for function. If you take a function from zp to the n to plus minus 1. So it's not only for p equals 2, but for every p. It's not exactly. I mean, I need to add some constants in some places, and some of them will depend on p. A polynomial depends on p, nothing too yes, but the basic proofs and techniques, everything goes along also for zp. Now, the remarkable thing here that essentially all of these proofs are going to be corollaries of a very simple lemma, which I'm going to show you. And then, so I'm going to show the lemma, and we're just going to present some of the proofs, assuming the lemma. And at the end, we're going to talk about the proof of the lemma, which is also not hard. So let's just state the main lemma. So again, suppose you're given some Boolean function with spectral norm A, And let's just add some notation here. F hat alpha would be the largest coefficient in absolute value, and F hat beta is the second largest. And let's just denote by this thing, F restricted to chi alpha plus beta equals Z, the restriction of F to this subspace, or F in subspace, if Z is equals -1. Then what I claim is that you can find B, I mean either 1 or -1, such that if you restrict F to the subspace on which chi alpha plus beta equals B, the spectral norm drops by at least A minus the absolute value of F hat of alpha, which is also at least A minus 1 over A. That's Parseval's identity. And if you restrict to minus B, then the spectral norm drops by at least F hat of beta. If you think about it like in a parity decision tree setting, then you begin with some function with the spectral norm A, and like on this side, you get to a subfunction whose spectral norm is A minus 1 over A, and on this A minus F hat of beta. Let's consider like the end function, for example. So the end function, it really has like one special point. Like on the old one input, it's -1, and in other cases, it is 1. So actually, it actually doesn't matter, I mean, which direction. In its Fourier spectrum is like it has this large constant term, like 1 minus 2 to the minus n or something like that, and all the others are really tiny. So, so if you think about the end function, it doesn't matter which direction you query. You're going to end up with a constant function 1 on one side of the tree, and on the other side of the tree, you're going to have just the end function on n minus 1 variables. So I mean, on this side, you pretty much gain nothing. I mean, just a really tiny fraction of the spectral norm. But on this side, you actually get to a constant function. Okay, is that clear? I mean, that's the lemma, but if you want... Okay.
Is there a lower bound on what F hat beta is? Because then you can show me something of this.
So yeah, so I mean that's so F hat of alpha must be at least 1 over A. That's you get do Parseval's theorem and you get what you get. The second one may be really tiny. I mean that's like the end function. So in some cases you almost get nothing. Okay, so that's the main lemma. So let's move on to some proofs. Just assume the main lemma is true. So let's prove this thing again. So I'm restating the theorem. You have a function with spectral norm A, and you want to find a subspace with codimension A squared on which F is constant. So it's pretty much obvious what I'm about to do, right? I'm just going to apply the main lemma and get a restriction whose spectral norm is A minus 1 over A. And then I'm going to do it again. I mean, right? But if it works one time, let's keep going. And after at most A squared times, I'm going to end up with a function with spectral norm 1, which must be a linear function. So if it's non-constant, then just again. So it's just really an iterative application of the main lemma, like A squared time, you get to the end of restrictions. And I'm just going to mention that this was kind of sloppy. If you actually try to figure out what's going on, you can see that the codimension of V is actually O of A. I mean, it's exactly the same algorithm. You just analyze it more carefully. And that's an independent work by Tsang, Wang, Shi, and Zhang. Okay. Let's show another thing that like the bound on the parity decision tree size, like 2 times n to the A squared. So the proof is simply by induction of on n. So let's define this thing like L of n and A. It's the maximum over all function with spectral norm at most A of the size of the decision tree. Like pick the worst function you can think of in this term with among all function with spectral norm at most A and take its size. So again, we use the main lemma. We like consider the tree which start by querying the chi alpha plus beta. So I mean, here we have L of n and A, on this side, the spectral norm drops by at least 1 over A, and the number of variables drops by 1. And on this side, we basically assume nothing, except that the number of variables is now n minus 1. And you basically just get this recursion, and you solve it. So again, also, you can do slightly better. I mean, you can get it to be 2 to the a squared times n to the a. And basically, the way you do it is that you weigh in the fact that either the largest coefficient is very big, like a half, or if it's less than a half, then also the second largest must be quite big, like 1 over 2a or something like that. So you just analyze both cases, and you push it down further to this thing. So this has two nice corollaries. The first thing that is sort of an analog to the Green and Sanders result. I mean, if you have a decision tree, you can just write it as a sum of indicators of subspaces by, again, just picking every leaf and taking the indicator function of this subspace. And the bound is 2 to the a squared n to the a. So recall that Green and Sanders has 2 to the 2 to the o of a fourth. I mean, it's sort of incomparable. I mean, so we have dependence on n, and obviously, I mean, the n functions show you can't, the size of the decision tree, even for function with small spectral norm, must depend on n. But you get a parity decision tree, which is nice, and also, like, if a is not super small, then actually this thing is better. I mean, for constant a, the Green and Sanders result is a. No, it is not known. So actually, their result is much more general. It actually works for every function from any abelian group, 0, 1, or even if it doesn't even have to be Boolean, but never mind. So for general groups, it is known that you need at least exponential in the spectral norm, but not for z2 to the n or zp to the n. So it's actually a good open problem to try to improve this thing to something better. Yeah, it may be polynomial. I mean, a second thing you can get is if you think of Boolean formulas, like you know, with AND and OR and NOT gates and bounded fan-in and all this stuff, then you can get a size 2 to the a squared n to the a times n squared Boolean formula for any function with spectral norm A. And then, since you can always balance formulas, you get this depth. So if A is constant, this means F is in the complexity class NC. That's the polylogarithmic depth and polynomial size, I think. So this is just you do an induction on the sides of the tree, and it's basically immediate. All right. So let's talk about learning theory for a moment. So our learning model is the following. We consider the pack model with membership queries, which is just the learning theory lingo for a black box access to a function f. And you measure your error with according to the uniform distribution. So you want to output with high probability and a hypothesis g with probability of x of f of x is not equal to g of x is at most epsilon. You want the running time, obviously, to be something good. So, I mean, polynomial in n, 1 over epsilon, and log 1 over delta. So this problem has been considered before. There's this very famous paper by Cauchy, Levitz, Mansour, which says that if a function has a spectral norm A, then you just take the a squared over epsilon largest Fourier coefficient, you truncate, write the largest, you take the sign, and that's an epsilon approximation for f. And what's even more important is that you can, using those membership queries, actually learn which are the largest coefficients and approximate their values. So you just output G as your hypothesis, and with very good probability in the time polynomial in n, 1 over epsilon, and log 1 over delta. Yes, but what if you insist on a parity decision tree for G? So, I mean, the most natural thing you can do is just query all these linear functions one by one, right? And you get a depth of a squared over epsilon. I mean, essentially, without knowing anything better about G, that's the best thing you can do. So what we do is we actually construct a parity decision tree. So you're given a function A, you have a black box access, and you construct a parity decision tree of this depth, which computes a function G, which is an epsilon approximation for F. So the running time is polynomial in n, in the size of the decision tree, which may be exponential in a squared, and 1 over epsilon and log 1 over delta. So I have here just this like table of comparison. So our hypothesis size is like obviously much larger. I mean, if you think of tree of depth a squared, its size can be polynomial in it can be exponential in a. However, it's sort of like you do much more pre-processing and you get a better hypothesis. You get these parity decision trees, which depth a squared plus log 1 over epsilon, as opposed to, I mean, here you have to query all the functions, so that's a squared over epsilon. And if you consider the case where your function is given as a parity decision tree, which is actually a case Cauchy-Levitin-Mansur considered, then this gives you a proper learning algorithm, or they give a polynomial threshold function. So let's see how we do it. So I'm going to define like a very simple thing. That's the bias of a Boolean function is just the absolute value of the probability that is 1 minus the probability that is minus 1. So like if the function is constant, this equals 1, and if it's balanced, it equals 0. It measures how far it is from constant. And we're going to use a recursive construction. So it's going to last at most k steps, where k is testing. It's just like a bound of the depth of the recursion I'm about to make. So I have two stopping conditions. One is I reach k levels, and the second is I arrived at a very highly biased function with bias more than 1 minus epsilon. And what do we do? Again, we just apply the main lemma, right? We do this thing, essentially. We arrive in some function with spectral norm A prime, and we query the two largest coefficients, and on this side we get A prime minus 1 over A prime, and here A prime minus G hat of beta, and all of this goes on for k levels. So let's try to analyze the error. I mean, what's going on here? So, I mean, several things can happen. I mean, on every level, you either make a good move, like where the spectral norm drops by a lot, or you make a bad move, where who knows what happens. And it may be the case like after about 3 queries, you arrive at a constant function, which is great. You just stop. You may be like querying all sorts of linear function, and this is where I ran out of Greek letters, so I chose chi eta, and you like get to -1, which is, so this is like grayish background. I mean, the function here is very biased toward -1, but it's not exactly -1. But again, you just stop. It's highly biased toward -1. And it may be the case that you query k linear function, and you get to a leaf where the subfunction can be almost balanced. I mean, no one knows what's going on there. So so let's analyze the error of this thing. I mean, where do the error come from? I'm just going to mention that, I mean, to prove the theorem, just take this tree and you replaced every leaf with the constant, like the majority value. So if you're constant, that's great. If you're highly biased, that's obvious what to do. And if you're almost balanced, then you just pick the majority. And also that, I mean, how do you learn it? You just, on every node, you just learn the two largest coefficients using Cauchy-Levitin-Mansur algorithm, and you move on down the tree. So we just left with analyzing the error. So we need to do this sort of like average over all the leaves. So these constant leaves are great, right? I mean, any inputs which follow this path is correct, because here the function is constant. These highly biased leaves are also great, because there's an epsilon fraction of all inputs which follow this path, which are incorrect, but it's only like a small fraction, so it's good. So like my only hope to save the day is just claiming that not many inputs arrive to these leaves. So, I mean, maybe half of the inputs which arrive here are incorrect. But what I claim is that there aren't that many inputs which arrive there to begin with. Yeah, so that's what we need to show. So again, let's figure out what's going on here. So on every internal node, you have half of the inputs following a good path, where the norm drops by 1 over a, and half of the inputs follow a maybe not good path, where I don't know what happens. So obviously, you can't follow more than a squared path, which reduces the norm without arriving at a constant function, because you begin with a and it drops by 1 over a on every step. So I mean, the question is, how many inputs make that many bad moves? I mean, you really have to make a lot of bad decisions in your life in order to get to a non-biased tree on non-biased leaf after such many queries. So recall k was 10 a squared. So like in expectation, you would expect that after 2 a squared moves, you would have a squared good moves. So the probability of following a path with such a high length without arriving to a constant is exponentially small in k, which is at most epsilon. Okay. Well,
Question. So when you're running, the exact two largest ones, but ones which are close.
Right, but I mean it's enough to approximate the.
So your minimum is robust to having not quite two large.
Yeah, even if you have approximation for the largest. You actually only need to know. You don't have to really know their values. You just have to know which two are the largest. But even if you're incorrect with approximated value and you get two which are not the largest, but large enough, it still works. Yeah. So again, I just repeat what happened. We had this recursive construction where we do it for at most depth k, or when we arrive to a leaf which is biased, and then we figure out that for at most epsilon fraction of the inputs, this tree is wrong. Yeah, so this is an example of a highly biased tree. You can see that. So let's just talk about the proof ID of the main lemma without giving all the details. So just remember what it says. You have this function with spectral norm a, and on one side you lose a minus the absolute value of f at alpha, and on this side f at of beta, where alpha and beta are the two largest. Just to make simplifying assumptions to make my life easier, let's just assume alpha is 0, and f hat of 0 and beta have the same sign. This is extremely not important. This is just for very less notations in those slides. It works anyway. So let's think what happened in the Fourier domain when you restrict a function on a linear function, on a subspace on which chi beta equals 1 or minus 1. So what I claim is that for every gamma, these two guys, f hat of gamma and f hat of beta plus gamma, they both collapse to the same Fourier coefficient when it's going to have this absolute value. I mean, either plus or minus depends on plus or minus here. So like before we can arrange them all in pairs, like f hat of gamma 1 and f hat of gamma 1 plus beta and gamma 2 and gamma 2 plus beta. These are basically just the, if you think of it, it's the coset of the additive subgroup, which is generated by beta, which consists of beta and 0. And after every pair collapses to the same coefficient. So let's consider what happens if we restrict on chi beta equals minus 1. Let's call it f prime. So before we had two coefficients, f hat of 0 and f hat of beta, and their contribution to the spectral norm was just the sum of those two values. And now we have f hat of 0 minus f hat of beta, and the contribution is this thing. So recall we had this assumption that they have the same sign. So like, think, for example, both are positive. So here you get their sum, here you get their difference. So you actually like for this pair, you saved 2 times the absolute value of f hat of beta. And recall, let's go back to this slide for a moment. So every other pair cannot increase, obviously, the spectral norm because of the triangle inequality. So every pair either sum or subtract from one another, so it cannot increase. So for this pair, we save something, and that's what we get. So obviously, this is like the easy part. I mean, the real action is if you restrict on chi beta equals 1. So I'm not going to do this. It's going to take some time. I mean, but I can assure you it's really simple. Nothing fancy going on there. If you want to see it, just come by later. So let me just state that essentially, again, everything I said also works for those kind of function, f from zp to the n to plus minus 1 for any prime p. You have to do like more technical work there to get things going. Basically, due to the fact that now the Fourier characters are not Boolean function, they take the complex roots of unity of order p, and now the coefficients are complex, so you can't really do this trick like assume they have the same sign or a different sign. You need to work a little harder, but it works. I mean, everything. So let's mention some open problems. So the first thing is exactly what John said yesterday. This conjecture, which was made by Zhang and Shi and Montanaro and Osborne. So for every Boolean function f, its parity decision tree depth is at most is polylogarithmic in the sparsity. So recall we had this called the parity decision tree is at most a squared time log sparsity. So I mean, it's true when a is small, like polylogarithmic in the sparsity, but in general, a can be as large as the square root, the sparsity. So this is still open. Apparently, it's been like floating around in quite a few circles, so I've heard. The original motivation for this thing was the log rank conjecture. If you consider function capital F of x and y is just this lowercase f, which depends on x or y, just like bitwise XOR. So for this function, the rank is exactly the sparsity of f. So we don't know much. We know several things. The first is that this cannot be too tight. This c must be at least log of 6 to the base 3, which is 1.63. If you're into that kind of stuff, I mean, you can probably recognize this mysterious constant, where it comes from. It's basically like the function which separates the deterministic communication complexity from the log rank. These are the construction. Another thing which is known, that this is equivalent to the following thing, which seems easier, that for any Boolean f, you can find the subspace V with codimension at most polylogarithmic in the sparsity, such that f restricted to V is constant. So again, here you require a tree with. I mean, this obviously implies this, because if that's the depth of the tree, then any path with this depth make f constant. This seems weaker, but it is actually equivalent. And you can even be more brave and conjecture that you can replace here f hat of 0 by f hat of 1, the spectral norm. This conjecture was made by Zhang et al. And again, if you consider the size of a parity decision tree for f, so it's kind of annoying. We have this exponential dependence on a. We want to get it to be polynomial in a and a. That seems reasonable. We don't know how to do it. And also, it was mentioned like improving the Green and Sanders result. That's a good open problem. All right, so thank you.
Questions or discussion?
Yes. Yeah, that was the proof of the other case of the main lemma, which I didn't show. But that's a good question. I mean, the part I showed works for any f.
So can you say a word about this?
Yeah, let's just do it on the board. So we had this assumption that out of 0, largest out of beta largest, and we also assume they have the same sign. So now we're considering that f double prime, which is f restricted to chi beta, equals 1. So again, we have this this collapse, right, of every we have a of gamma and f hat of gamma plus beta, and each those two basically collapse to the same one, this time with a plus. So the loss comes from pairs with different signs, right? Because this time if they have the same sign, then the sum is just the sum, and if they have different signs, you lose something. So what you want to bound is like bound the sum over gamma, such that f hat of gamma f hat of gamma plus beta is negative of the minimum among those two guys. Right, because if they have different sign, and I add them together, then that's what I say for every pair in the spectral norm. Up to a factor of 2, I may be like counting twice each pair, but never mind. So maybe I'll switch to that side. So here's the crucial part. Like when you use the Booleanity of f, you claim that f squared is equals 1. That's obvious. And in the Fourier setting, that means that for all non-zero beta, you have that sum f hat of gamma, sum over gamma, f hat of gamma, f hat of gamma plus beta equals 0. That's convolving f hat with itself. That's all non-zero beta. So okay, so I'm not going to do the calculation, but you have here like when gamma equals 0, you have 0 and beta, and when gamma equals beta, you have beta and 0, and you get that like f hat 0 times f hat of beta is at most the sum over those gamma, which are negative. This product. And okay, so I'm actually doing the whole thing. Never mind. And this is most. So we call that f hat of beta was the second largest, and yeah. So I mean, like to take absolute value, and this is less than f hat of beta times what I wanted to bound. Okay. Any other questions? All right. Okay.